Greetings, class. This is Dr. York-Hammons working another example from Chapter 8, Section 4. I'm on page 452 of your e-text, looking at problem number 13. This is about building new nuclear power plants in the country. So we're going to use this figure that talks about the percentages from each country. So it shows the percentages of adults ages 16 to 64 from the U.S., Great Britain, France, and Spain who favor building new nuclear power plants in their country. The survey included random samples, that's important because we need to know they're random, of 1,002 adults from the United States, 1,056 adults from Great Britain, 1,102 adults from France, and 1,006 adults from Spain. So number 13 is referring to the United States and Great Britain. So we're only going to be looking at these top two percentages. It says at a level of significance, alpha equals 0.05, that's 5%, can you reject the claim that the proportion of adults in the United States who favor building new nuclear power plants in their country, the USA, is the same as the proportion of adults from Great Britain who favor building new nuclear power plants in their country? So that's our claim, is that the two population proportions are the same. Now, when they say the same, they mean the two population proportions are equal. So in this case, I'm letting P1 represent the U.S. population proportion and P2 represent Great Britain population proportion who favor building new nuclear power plants in their country, and those are adults ages 16 to 64. Now, the word the same means equal, so our null hypothesis is our claim. The alternative hypothesis is the complement to equal, so it is not equal. So this is the hypothesis, the null and alternative hypothesis statements that you would use in my stat lab when it asks you to state the hypothesis. Now, the next thing that we normally look for are critical values. So I need to open StatCrunch so that we can find critical values. Now remember, critical values are using a calculator. So we go to Stat, we use the normal calculator. Now remember that when it's a not equal, that is two-tailed. So I have to use the between function on the calculator, on the normal calculator. Now normally, if it's one-tailed, we use the value for alpha. But when it's between, I have to use 1 minus alpha. Well, 1 minus 0.05 would be 0.95. And when I click compute, it gives me those cutoffs for the rejection region. So in this particular case, I'm going to do a little snip of this particular graph so that I can make some adjustments to it for you. I can actually shade in yellow the areas that would be the rejection region. So the yellow areas are my rejection region. If my test statistic, my Z statistic that I'm going to get in a minute from the proportion stat test, if it's less than 196, or greater than, less than negative 1.96, that would be right here, or greater than a positive 1.96, that's this area right here, then I know that I'm in the rejection region. So I'm going to copy this and go back to my Word document that we were looking at. And I will add that to the document because what I want to do is to use this picture to, I'm going to make it a lot smaller so that we can actually write beside it, is that I need to write my, I need to do two things. I need to do the critical values for z sub 0. Those are, since it's two-tailed because it's not equal, this, remember, this not equal here means that we're going to do a two-tailed normal calculator distribution. So it's two-tailed test. So the critical values are negative 1.96 and 1.96. So the rejection regions that you see below there in yellow are if your Z test statistic is less than negative 1.96, which is this yellow area to the left, or if your Z value that you get is greater than the positive 1.96, and that's this area on the right. So we'll be, when we look at our test statistic, we're going to look, is it to the left of negative 1.96, or is it to the right of a positive 1.96? So we're going to go back to StatCrunch, and we're going to actually do that particular test. So to run the test, I go proportion stats to sample with summary, because they didn't give me a column of data, they only gave me some percentages here. But it asks me for the number of successes and the number of observations. Well, I know for the U.S. that there were 1,002 adults, and for Great Britain, there were 1,056. But I don't know the number of successes. I simply know these percentages, the p hat, that's the sample percentage, and so I need to figure out how many successes 51% would be. To find that, I use my calculator, and for the U.S., I'm going to look at 51%, which is 0.51, and I'm going to multiply that by my sample size, my number of observations, 1002, and I get 511.02. So I'm going to round that to 511. Now I'm going to do the same thing for sample 2 for Great Britain. I'll move this down so you can see. Great Britain is 50%. So for 50%, I'm just going to clear, what I typed in. I'm going to do 0.50, 0.50 times 1,056. That's the sample size for sample 2, and I get 528. So I had to calculate the number of successes by multiplying my percent, in this case 0.51, times 1,002. And for sample 2, to get this 528, I had to multiply my 50%, 0.50, times 1,056. Now, my hypothesis test, let's pull that Word doc back up so we can see our claim there. So it was not equal. Oh, and that is the default, is not equal. I'm going to store that information in the data table. Move back over where we can see our problem again. and I'm going to click Compute. Now you will notice that our z-stat value is 0.4526 or 0.453 to 3 decimal places. So let's look at that Word doc and let's make a note that our z-stat was equal to, and I'm going to get that back down to 3 decimals, that 2 will become a 3, was equal to 0.453. Now, since it's positive, we would check the positive value here and compare our z value to 1.96. Now, you could also come down to the table and realize, come down to the distribution, the normal calculator. Our boundary, our critical value was at positive 1.96, but 0.453 is actually over here, and it's not in the rejection region. So we know that z is actually less than 1.96, but it's not negative either. It's between 0 and 1.96 here in this area that's not part of the rejection region. So it is not in the rejection region. What that means is we fail to reject H sub O. So this is one way to determine whether you can reject a claim or fail to reject. In this case, we fail to reject H sub O. Now, the book doesn't, or excuse me, my stat lab doesn't always ask you to compare the rejection regions. Sometimes it allows you to simply use the p-value. And the p-value here is 0.651 to 3 decimal places. So I'm going to copy that, and we're going to go back to our Word doc, and we're going to talk about the p-value. Oops, back up here close to the problem. So when working with the p-value, if the p-value is less than alpha, and that's this value right here, alpha, that looks like a little a, equals 0.05, then reject HO, the null hypothesis. If the p-value is greater than alpha, fail to reject H sub O, or H naught, or the null hypothesis. So let's check. Our p-value was equal to, I'm going to break this down. We said 0.6508, which would be 0.651. And we're going to compare to alpha, which is equal to 0.05. So we're asking our question, is the p-value 0.651, oops, that's not supposed to be negative, 0.651, is that less than 0.05? Well, no. So I can't reject H sub O. But it says if the p-value is greater than alpha, so I ask myself again, well, is 0.651 greater than 0.05? Well, that's yes. So we fail to reject H sub 0, or H naught, or